All right, so I'll talk about experimental work done with Lior Ella, Asaf Rosen, Debargo Duda, and Shachar Alani. And all of this work was made possible by the graphene devices made by John, David, Moshe, and Andre Geim from Manchester. This is a bit more relevant to the next talk, but theory support from Thomas Gafidi from Berkeley, and then from Weizmann, Tobias, Raquel, and Adi. Okay, so the idea is to try to experimentally probe something to do with electron hydrodynamics, but as we learned yesterday from Lawrence Molenkamp's talk, really a lot was done already decades ago in terms of experiment, which you see here on the right, and theory as far back, maybe even further from the 60s from Gurji. So the question is, what's left to do, right? They already observed hydrodynamics in experiment. Well, this was a few decades ago already, and what's recently available are new clean materials. So most relevant for us is graphene. So this is a summary of the recent transport results in graphene in the last couple of years that re-looked at some of the same questions, but now with new materials, there are new kinds of experiments you can imagine. And then additionally, there's nice work in palladium cobalt oxide from Andrew McKenzie, and also tungsten diphosphide as well. But I want to emphasize that these are all some form of transport measurement, right? So you attach fixed leads to a sample, you pass some current or heat through the sample and do some transport measurement. You don't really get an idea of what's going on spatially, but you like to think of hydrodynamics as something that can produce really beautiful pictures and has all sorts of interesting spatial phenomena. So it seems really ideal to try to think about these things in terms of a scanning kind of measurement. So there's very well-known predictions for, say, looking at voltage features from Levitov and Falkovich, shown here. This is the idea is that if you have some source and drain in the diffusive regime, the way the potential drops across the sample is kind of expected, sort of linearly, right? Whereas in the viscous or hydrodynamic regime, you can get these vortices and have negative local potentials that you can't get with just diffusive flow. And I'll show some examples later of experiments that try to actually look at these kind of effects. But I want to emphasize that while this is a valid prediction, certainly for hydrodynamic flow, there's typically for all of these predictions for how something should manifest spatially in terms of a voltage pattern, say there's an equivalent experiment or an equivalent phenomenon that will happen for just ballistic physics completely, right? And in fact, the ballistic version is typically a much stronger signal, right? So you can get these exact same kind of patterns for just ballistic flow, nothing to do with hydrodynamics. And then you're left with trying to distinguish between, the experimentally relevant regime is looking at the ballistic to hydrodynamic crossover, right? So diffusive physics should be pushed out of the picture completely. And then you're asked to distinguish between, say, voltage vortex from ballistic flow versus a weaker version of that in hydrodynamics. So you can't make a strong case for hydrodynamics from this sort of thing. Although, as I'll show, there's still really interesting ballistic effects that arise. So then instead, also, this is what Amir talked about at the end of his last talk. The other obvious thing to do is to ask what does the actual current profile in a graphene device, or rather a hydrodynamic electron device, look like. The cartoonish picture of Poisson flow, I think that's how it's pronounced, is this parabola. Whereas in diffusive regime, you won't get this parabola. So if you could actually image this and make a strong claim that this is you really understand what you're imaging, then maybe this is a very nice spatial picture of hydrodynamic flow. So I'll jump to the conclusion of tomorrow's talk, just because I know not everyone will be here, and just show you what we're going to build up to. So these are actually our experimental plots, two-dimensional flow maps of current, flowing through a graphene channel right here. So the width of this channel is 5 microns, And at 4 Kelvin, we see a flat profile near the center of the channel, right? So this is something to do with the current flow. I'll describe all of these details later. When we heat to 75 Kelvin, we see this nicely parabolic Poisson current profile. And we see this in, it's not just a line cut here. We see over, a large section of the device, across many devices, in fact, across a range of temperatures. We can tune this transition. I want to note that we don't have to invoke any sort of deconvolution procedure, and we'll describe why that's the case. So this is a pretty direct measurement of this that doesn't invoke any model. And we can also explore the ballistic to hydrodynamic crossover in addition to the, where diffusive transport fits into this. But you should ask yourselves already, to be a critical audience and say, like, to what extent should I trust any of this? I didn't mention anything about the mean free path in the sample or what's going on at the boundaries. So these are very important things that we're going to address. But in addition to that, there's concerns also about, what are we really measuring with our technique? Do we really understand the signal? And we're going to answer all of these questions. But the focus of today's talk is going to be on developing the technique that we use to actually do these kind of current imaging experiments. But I want to emphasize further that this is a measurement done of actually a voltage that we're so we're actually imaging a spatial voltage. So it sounds a bit counterintuitive at this stage. How by imaging voltages are we going to ultimately get to some current profile? So this is what I'll describe now. So if we want to ask what's a good tool to image nanoscale voltages of flowing electrons, we want to have a couple of features. So modern versions of devices, namely the van der Waals materials, are buried typically between some protective overlayer, right, or beneath some overlayer. In graphene, it's boron nitride. This is to maintain the high mobility and keep impurities from disrupting the flow. So we want a probe that can image beneath buried insulator. In addition, we want to have high voltage sensitivity, right, because some of these for ballistic effects, of course, can be very subtle, but hydrodynamics as well, and we don't want to have to blast our device with a huge current or something and then this can, raise a lot of doubt as to what we're actually measuring. So we want to be able to resolve very, very sensitively small voltages. So, of course, there are optical techniques, more exotic probes for imaging these kinds of things, but the leading probes for directly imaging potentials is basically a version of scanning tunneling microscopy called scanning tunneling potentiometry, as well as Kelvin probe. So each of these has one of these two features, but not both together. So this scanning tunneling potentiometry, because so you can image very small voltages with this. So this is a graphene device here, and they apply some bias across and use the STM tip to infer the local potential drop in the device. And you can see here that the scale is on the order of microvolts. Okay, so this is very nice. Of course, has very nice spatial resolution as well, but this limits you to surfaces that you can directly tunnel into. So for any of the high mobility graphene devices, things like this, you can't use this technique because you won't have any appreciable tunneling current to go in the sample, and you won't have any signal. Kelvin probe, on the other hand, has no problem imaging things beneath the surface. But, so this is an older measurement from 2000 of the potential drop in a carbon nanotube. And you see that the scale of the voltage that they apply to the device is 100 millivolts. And you can see the noise level here. It's several millivolts. A more recent result from Philip Kim's group, doing the same kind of measurement with a Kelvin probe, but now on a graphene device, they're applying 2 volts across the device. So this is not a relevant regime at all for us for the measurements I'll describe. So we want something that's much more sensitive than this. But additionally, we want to be minimally invasive, right? We don't want to have our probe disrupting the physics that we're trying to explore. So a variation of Kelvin probe, or not a variation, but based on the same scanning technology, is something called the scanning gate. So this operates in the opposite limit of being maximally invasive. Right, so here you flow some current through a device. You try to use the tip to locally deplete or gate the sample, and then influence the flow and try to measure, say, a global or a macroscopic change in the resistance of the sample as a function of the position of the tip. So you can do things like exploring cyclotron orbits in graphene, but this is linked to pretty particular flow geometries, and again is sort of maximally invasive, and we want to be in the opposite limit. While we're at it, if we're going to look at electron hydrodynamics, we need to be able to operate across a broad temperature range, because at the lowest temperatures, the phase space for electron-electron scattering shrinks to 0, so you don't expect any hydrodynamics there. This is a phenomenon that is going to emerge at higher temperatures. So we want to be able to scan, from cryogenic up. And I might as well throw in operating in magnetic field too, just because there's lots of interesting things you can do with magnetic field. And it turns out that's a crucial aspect of our work. So a good place to start is looking at what's the most sensitive scanning detector of voltages that exists, and that's the scanning single electron transistor. So this was largely pioneered by Amir Yacobi. This is a representative experiment where they used a scanning single electron transistor, or SET as I'll call it, on the end of a sharp tip, and they used this to measure the disorder landscape in graphene. So the idea, which I'll describe in more detail in the following slides, is that you have a quantum dot essentially at the end of this, and you use the Coulomb blockade physics, which has very sharp peaks in the current as a function of the local potential, to transduce the local electrostatic environment into a measurable signal through the detector. Okay, so our modern take on this is a nanotube-based scanning single electron transistor. So the device is made in a bit of a weird process, but allows us to make really clean nanotube devices, which are useful for a broad range of experiments beyond scanning experiments. Just if you're interested in looking at super clean 1D systems, it's a really nice way of producing them. But the idea is to grow nanotubes on one microchip across trenches, and then to make a second microchip which has an array of electrodes on it that are patterned into a cantilever geometry here. And then we use a scanning probe microscope to scan this chip with respect to, this cantilever chip with respect to the trenches, to find a nanotube and then place it precisely on the end of the cantilever. So what does this actually look like? So it's not really a cantilever in the sense that this beam isn't freely oscillating. It has a ground plane everywhere, which is actually useful for the scanning measurements to control the electrostatic environment. But at the end, if you zoom in, you see there's a source and drain electrode, and this is at the corner here, and there's a local gate here which is recessed below the source and the drain, and we are then able to place precisely a nanotube at the end here, and this is what forms our detector. So this is the scanning SET. Okay, so how does it work? So here's a cartoon of the cantilever. You see its local gate with the nanotube here, and this is over some prototypical graphene device that has graphene sandwiched between insulating HBN layers with the backgate here that can control the overall density in the sample. And we have a zoom in here, so you see the source, the drain, the nanotube, the gate, and electrons can tunnel from the drain onto the nanotube, or rather from the source onto the nanotube and out. So the idea is that no charge is going to be transferred directly between the SET and the surface. Instead, we're measuring transport through the nanotube in response to what's going on in the surface. So how does this work? So at low temperatures, the band structure of the nanotube will look like this in response to putting a voltage on the gate here. So you'll have holes in the leads, a tunnel barrier here between the source and the drain and the gated region, and then an electron quantum dot here. And so then these electrons can tunnel in and out to the leads. So this will exhibit typical Coulomb blockade oscillations. So you can imagine if you tune with the local gate to be on the side of a Coulomb blockade peak, this is going to be, because these are sharp peaks, this is going to be a very sensitive probe of the local electrostatic field. So you can decompose this. So this is plotted here as a function of charge, and you can decompose this into potential electronic effects and capacitance or mechanical effects. For mechanical effects, we're able to look at things like domains, ferroelastic domains, piezoelectricity, and materials. This isn't going to be relevant at all for this talk. Instead, we're going to focus completely on the ability to image potentials with the SET. Okay, so I'll review the equilibrium electronic imaging modes of the SET first, and before moving on to how we distinguish the flowing electrons from these equilibrium quantities. So the most basic measurement you could imagine doing with the scanning SET is to try to image the local disorder potential, or the work function. So here's a cross-section of this graphene device here, and you can imagine a piece of junk on the surface that, like any small piece of stuff, will have some residual charge on it. So the potential of this is going to vary in space, and the idea will be to apply a feedback voltage to the local gate here as you scan across to maintain constant current through the SET. So as you do this, then the voltage that you apply here is going to be directly related to the potential on the surface. So what does this actually look like in experiment? So here's an optical image of this device. Graphene is everywhere in the image. The leads are outside of the image. And the dashed lines here are marking where the graphene has been etched. So electrons can enter here. So there's a contact over here, and they can flow through here, bounce around, and come out. But now we're just going to scan this with this feedback mode that I just described. And we get an image like this. So you can see that there's larger fluctuations where you have etches. And this makes intuitive sense, right? Where you've chemically etched the graphene, there's going to be more disorder, and this will give you larger potential fluctuations. In the bulk of the device, you see the potential fluctuations are much smaller. So I want to, oops. Okay, yeah, I just point out that the scale here is millivolts, so it's pretty clean sample in the bulk. So this is super important for the hydrodynamic experiments that we'll get to eventually. So the next standard mode of imaging an equilibrium quantity for scanning SET is something called the electronic compressibility. So now we're going to apply an excitation to the backgate of the sample and measure the amount of the voltage or the electric field rather that penetrates through the sample and that is then recorded by the SET. Okay, so if you have a perfect metal here, then the perfect metal will completely screen all electric fields that you apply to the backgate, and you won't see anything. But real material like graphene has a non-infinite density of states, right? So this is going to actually probe the density of states directly. So the amount of field that penetrates through is really a direct probe of this band structure quantity. So what does this look like again in experiment? So we can scan across the device, and keep in mind where the device has been etched, you'll have full penetration of the field. So you see in the experiment, the image is kind of dominated by this the field penetrating through the edges, but we're going to focus on what's going on in the actual graphene part of the device here. And so we can actually park the SET just at a fixed position, and then scan the density by tuning the backgate voltage, and you can map out the inverse density of the density of states of the graphene with this, or more directly d mu dVBG. Okay, so this is a very powerful tool. Many experiments have been done using this idea, but we want to now move beyond both of these equilibrium measurements and try to image the potential of the flowing electrons. Okay, so this is also pretty straightforward, and it's analogous to what's done with Kelvin probe. So now we'll look at the cross-section of the device again, and we'll imagine applying an excitation on one side and passing current through. And you can imagine that there's some barrier to flow in the device, all right? So this can be like this etched constriction here, for example, can represent some resistive barrier. And you can consider this as a series of resistors, most simply, right? You have some small lead resistance, a very large resistor here where you have this constriction, and a small resistance to ground here. Okay, so what will the potential look like? Or rather, how does the voltage drop across this device? It'll be relatively flat here and here, and then drop sharply here where the resistance is largest. And we can then record the response to this excitation as a function of position. So this is, it's, if you want to think about it in a different picture, we're measuring the local capacitive coupling to the sample as a function of position with respect to the excitation applied here. But we can, of course, do this symmetrically. We can apply an excitation to the drain as well, measure exactly the same thing coming from the opposite direction. And then we can combine these two signals to form something we're calling the potential of the flowing electrons. So by construction, this quantity is going to be the value of the excitation far over here at this lead, 0 over here at the drain, and will vary in between according to the potential of the electrons. What do I really mean by the potential of the electrons? I mean that, if in a semiconductor, this is like the bottom of the band that's moving. Or in graphene, for example, the position of the charge neutrality point in space. Okay, so this is really what we're mapping here. So it's the electrostatic potential. It's not the chemical potential or electrochemical potential or anything like this. It's the electrostatic potential. So this is the picture to have in mind. Okay, what does this look like in experiment? So again, we take this same device. We have a constriction here. We can inject electrons. They can bounce around here, however, eventually find the constriction, come through, bounce around in here, and then leave through the other constriction. And in experiment, we see that we see 3 nice plateaus of potential. So why do we see this effect? You can, again, because the resistance of this device is dominated by the constrictions, the potential is basically constant away from the constrictions. So the electrons have one potential here of the source, which is 1 millivolt. Then the potential drops here to another fixed value, and then back to ground here. And I want to stress that the scale of the measurement here is now in microvolts, and we only apply 1 millivolt to the sample. So if you want to contrast this with the Kelvin probe measurement I showed earlier, this was a comparable kind of device where 2 volts was applied to the device. So now we're really more than 1,000 times more sensitive. And anytime you have a tool that's orders of magnitude more sensitive, you can do new sets of experiments. So I just want to go over exactly how well this performs now to give you a sense of how to compare it to other things. So go through a brief technical description here of how we benchmark the SET. So the first thing someone probably asks is, what's the spatial resolution of the SET? Okay, so now our current measurements were at about 100 nanometers, but I'll show you that there's really nothing fundamental about this. So how do we get to this number? We can have some feature in a device that we apply a potential to. This is experiment. We scan across the feature. We measure how the potential step rises from one side to the other, and then we can fit the function here and get the point spread function width. So this is so by 100 nanometer spatial resolution, that's what I'm describing here is the point spread function width. But if we see that how by basically measuring how this scales with scanning height above the sample, we can see that we're essentially limited by how high we are above the surface right now. So if we're able to get much closer, the point spread function should get much smaller until you're limited by the lithographic dimension of the device. But there's no fundamental limit on this either. If you shrink the source and the drain electrodes separation, which you can do easily lithographically, then this could easily be improved, down to 20 nanometers, say, without much effort. You just have to be pretty confident that you can scan this microchip with respect to the sample without crashing them into each other. And that's what what's limiting us right now is basically we don't want to destroy our experiments. We haven't been super brave yet, but so we're hovering at 100 nanometers for now. But in the future, we can push closer and probably see new set of physics. But it doesn't really matter actually for now. There's plenty of things you can see on the 100 nanometer scale and above. So the other obvious question to ask is, what's the actual voltage sensitivity? Well, I hinted at it in the last map by showing the scale bar was in microvolt units, but what does that really mean? You can use the simplest model where you just measure the noise, current noise through the SET, and normalize this by the gain of the SET with response to its local excitation, and then divide by the bandwidth of the measurement, and we get about 2 microvolts per root hertz. And we see this pretty consistently across a range of devices. The other important aspect for this work, again in contrast to techniques like scanning gate, which are super invasive, we want to perturb the flow as little as possible. So this kind of device geometry gives us a nice way to intrinsically calibrate how invasive we are, because these constrictions here are very sensitive probes themselves of their electrostatic environment. So you can imagine if you scan our nanotube over this device, when you scan it over the constriction, you might very strongly change the resistance through the graphene, right? So if you measure the 2-point resistance of the graphene, shown here as a function of density, and you do this measurement as you scan the nanotube across, and now map the resistance of the graphene device as you change the position of the nanotube. So this is essentially what a scanning gate measurement does. So this shows you how our technique in this mode would be a very poor scanning gate, because the change in resistance through the device is on the order of 1 part in 1,000, right? So this corresponds to invasiveness in terms of density fluctuations of less than 1 × 10⁹ per centimeter squared. And this is below the fluctuations of disorder in the sample anyway, so we're not perturbing the sample at all with our probe. However, in fact, if you wanted to do scanning gate with this, you could easily. You can apply whatever large voltage to the device you want and intentionally gate it, but we have this flexibility. So if you want to use it as a gate, you can, but even better, to tune things such that you can be as minimally invasive as possible. One other nice feature, which again is crucial for imaging and the hydrodynamics, is that we need to be able to image across a range of temperatures. In fact, this will work essentially in ambient conditions, in air, room temperature, not as an SET, but as an FET, so a field effect transistor. Because the nanotube is a semiconductor, you can tune it to be on the mobility edge between conducting and insulating. And by using the same sort of feedback tricks, you can image in ambient. So we have now just a simple demonstration of this. We haven't probed this much further yet, but we have a piece of graphene here with some electrical contacts. You can apply a voltage to it and measure with an AFM what this thing looks like here at the end, and compare this to the image taken in air with the SET at room temperature, and it looks looks the same. So it works in ambient conditions too. Okay, great. So now we've described how the SET works, exactly how well it performs. So let's actually apply it to some real things and see if we can see some interesting physics. Okay, so the geometry that's going to be most relevant to the flow experiments, which we'll get to later in the hydrodynamic regime, is a channel geometry. So we have a gold contact here, another contact here. This is an optical image of the actual device. And here we have etched walls that are shown in blue. Okay, and the graphene is everywhere else, and it's sandwiched again between boron nitride. Okay, so the 2-point resistance of this looks like this, right? This is at 4 Kelvin. It's very sharply peaked because it's a super clean device. And we can ask, what does the potential look like, or rather, how does the potential of the flowing electrons drop as a function of density? So in the ohmic regime, so we tune to via the backgate to as close to charge neutrality as we can get. And you see exactly what you would expect. The potential drops linearly, and this is completely indicative of ohmic transport, right? This is what you would expect. But now, more interesting, let's tune to a larger density here into the what should be the ballistic regime, and we get this nice picture here. So we were really excited by this because this is like a textbook picture, right? If you look in any introductory mesoscopic transport book, they describe ballistic flow as having all of the resistance is at the leads of the device, and it's constant potential in the bulk of the device, right? But and you can measure things via transport that suggest there's ballistic flow, but can you actually see it in real space? Does it actually look like that? And the answer is yes, it really does. So this is all enabled by the fact that we can apply really small excitation. So this is only a couple of millivolts across the device. So we're not doing any crazy heating or.
So can you use the finite slope to extract what is the fraction of electrons who are ballistic and what which are not?
Yeah, I mean, yeah, that's not exactly how I would phrase the measurement, but this measurement, yes, exactly. So that's why I'm mentioning next, actually. So beyond just making a pretty picture that confirms your expectation of what you hope to see in a ballistic regime, for example, is you can do this measurement, or rather you can say pick some line in the middle of the device, for example. And now you can analyze the voltage drop along this line. And what this corresponds to is essentially a completely contactless 4-probe measurement, right? It's like we can do any measurement that you can do via transport where you have fixed contacts. We can do this everywhere in space without the need to lithographically define contacts. And lithographically defining contacts can often be pretty problematic, because especially in the ballistic regime, right, you have all sorts of mesoscopic effects where the electrons can bounce around in very geometry-dependent ways at the leads of the device, and we want to remove this uncertainty completely from our measurements. So now we can measure the voltage drop without any perturbing contacts or leads.
You mentioned that you measure the electrostatic potential.
Yeah. So this is like the right. So if you were measuring if you were to ask what the chemical potential here would be, it's not necessarily the most well-defined question, right? You know what the chemical potential is at the leads, but not in the middle. But just 1 second. But the electrostatic potential is well-defined everywhere. And
yes, but the analogy is just additional terminal. It's not exact, because terminals measure electrochemical potential, electrostatic potential.
That's true. It's a fundamentally different quantity. I think you could argue that it's sometimes more interesting to think about the electrostatic potential than the. Yeah. Okay. But yeah. So you're right. You're right. No, it's a good point to emphasize that it's not measuring the same thing as a transport measurement. That's for sure. Okay. So we can then quantitatively extract the conductivity, and then of course relate this to mean free path of the sample, but. We'll hold off on how to actually interpret these measurements for the next talk, because this is really non-trivial in this regime here, where you are close to ballistic in the sense that you should have few impurities in the channel, and at low temperatures no phonons, but you have what we'll claim to be our diffusive walls. So the resistance is really coming from the walls, and so you need to understand how electrons are scattering off the walls versus the bulk. And so for that, we're going to rely on magnetotransport measurements, but again, scanning versions of those, which we'll show in the next talk. But I just want to have you keep in mind that we can do these intrinsic 4-point measurements at any place in space. Okay, so now let's go to a more reminiscent geometry of what I showed at the beginning of the talk with these voltage vortices, right? So we thought that it would be really cool to have a kind of drag geometry, right? So this is another optical image of a graphene device where you have etched walls here, here, and here. The graphene is everywhere else. The contacts are outside the image. And at some point here, we have an etched, or rather an opening between the two channels. Okay, so you can flow current here and ask what happens up here. So the inspiration comes from real fluid experiments, where you can do something like this, right? You can flow some particles across some notch and see that you create this vortex of matter here, right? So could you really do this with electrons if they're hydrodynamic, right? This would be super cool. So what does this look like in measurement? So we flow electrons here. we measure what's going on with the SET, or rather image the potential of these flowing electrons in this box here around the slit, and this is where this slit is here. And this is the actual map of the local potential. And so you see, okay, it's linearly dropping here, as you would expect, but what's going on up here, you don't really see anything. That's just, that's just because the most prominent feature is the voltage drop here. But if you rescale the colors, you'll see that in the diffusive regime, where you're close to charge neutrality, you see basically linear potential drop up here as well. Okay, nothing too interesting. But now we'll look in the ballistic regime, and you see that actually, the red and the blue here is now mirrored up here, but the red is on this side and the blue is on this side, right? So in the ballistic regime, it looks like, okay, you have this kind of voltage vortex sort of thing, or at least a non-local negative voltage, which was the prediction for the hydrodynamic physics, right? So let's just take a look at the scale of this. So the green is the potential drop along this line cut here, and the black is the potential drop across this line cut here. And you see, okay, first they're in opposite directions, so that's nice. And the scale of this drop is only 30 microvolts. So again, this is something that you really need this sort of sensitivity in order to resolve, because conventional technique won't allow you to image this spatially. Of course, you can do a transport measurement and just have a fixed contact here and here, and you'll measure a non-local resistance. But the point is to say, like, how does it actually vary in space? So I think this is the first time something like this has really been mapped out. But again, this is a ballistic effect, nothing to do with hydrodynamics, right? So what's actually going on? What's behind this physics? Very intuitive to understand. In the diffusive regime, you can't have any local maxima or minima of the potential, right? So the potential can kind of bleed into the upper region here weakly, but it will sort of linearly fall along the main current path. In the ballistic regime, however, you'll have direct sort of line of sight from the carriers emitted from the contact here, which will deposit their potential here over here, or imprint rather their potential from here over here, and the same thing happening from the other lead, imprinting the potential from here over here. And so this is the intuition as to why the potential is reversed in the ballistic regime. So basically, anytime you have these ballistic trajectories, they're going to give you these kinds of complicated voltage patterns.
Does it depend how close to the neutrality point?
Yeah, exactly. That's exactly the difference between this image and this image. So this image is far from the neutrality point, and this is at the neutrality point. Yeah.
Just again, point to the nomenclature though. By diffusive, you mean what other people would call ohmic?
Yes. We used to call it ohmic also. I actually also prefer calling it ohmic. That's just the word that comes to mind. But I think other people quibble with this, so we're going to call it diffusive. But it means ohmic, yes.
Just not obvious, why do you expect to see anything in hydro regime? Because the effect which you show, it's rather current flow, but you mapping the voltage, and in hydro regime current and voltage not so,
It's true. They're not exactly the same. You can imagine having scenarios where the voltage doesn't have some kind of swirly pattern, whereas the current does. But in this specific experiment, if you apply the accepted models for hydrodynamics, you would also get a voltage signature here too. That would, we can show you simulations that we have of this exact kind of geometry. I mean, that's where we really started with those experiments in mind, and it's all swamped by ballistic physics.
The boundaries are electrostatic, or?
No, they're etched. Yeah. So that there's no graphene at where the blue is. It's been chemically etched away. Yeah. Right. Okay. So we can also simulate this. A ballistic simulation versus a fully diffusive simulation, and you can ask, is this really what's going on? And our simulation matches the experiment very nicely. So we think this is a cute short story or demonstration of these ballistic effects, which can sort of mimic things that you would expect in hydrodynamic, but much more strongly and much more trivial to observe, right? This is, you don't have to do much playing around with materials. As long as you have this super clean graphene device, you can very quickly start exploring this cool ballistic physics. And I also want to stress that there's, hydrodynamics is of course very interesting, but there's a huge amount of ballistic physics that is sort of 90s era mesoscopic physics that has been a bit abandoned to an extent because all of the experiments were done with transport. But now that there's these new materials and new techniques, there's new ways to explore some of these things and to see what's going on spatially and revisit, are there any open questions for this? Okay, so now the last part here, which is most relevant to the next talk, is how we use this voltage imaging technique to image current. Okay, so just like we apply some current flowing across the device and measure the voltage drop associated with this current, we can now do the same kind of measurement, but in the transverse direction here, in the presence of a weak magnetic field. So the trick is to basically use the Hall voltage to infer something about the current. So like in the most basic description of a diffusive conductor or an ohmic in the ohmic regime, that you have a local simple relation between the current and the Hall voltage, right? So measuring the Hall voltage tells you what the current is, right? So let's try to do this spatially. Okay, so now we'll take a device that's similar but a bit different geometry. So we have, again, these etched barriers in the graphene, and you have a source here, a drain here, so the electrons can flow in and come out here. And we're going to focus on what's going on in this box here. And so we're going to apply a weak magnetic field and see how does the Hall voltage manifest in space. Okay, so these are the equipotential contours in plus or minus 20 millitesla. And at 0 millitesla, these would be these straight line or vertical lines like this in this part, but now they're at this large angle. So this is a real space mapping of the Hall angle, right? So this is also, I think, something that had previously not been seen in space, right? Does the Hall effect really look like this in space? Yes, it does. It's nice, but it's not just nice, it's also useful in the sense that you can now take the difference between this map and this map, normalized by the Hall resistivity, and this can be related to the current density. So in fact, this quantity here is really the streamlines of the current. Okay, so let's do this now. Let's just take this image, or rather this image, and subtract from it this image, and see what we get. So the difference between these is the black lines plotted here. So these black lines are exactly the current streamlines of the electrons flowing through. So you see the current really goes this way and flows around the bend as you would expect. But simultaneously, we're also measuring the voltage drop as well, and that's what's plotted here, the zero field voltage. So you see that the current streamlines are perpendicular to the voltage contours, right? As you expect for Ohm's law, right? Okay, but this is, I described all of this with a diffusive picture in mind, right? So you can ask, in what regime is this valid? So let's explore this a bit more quantitatively. So consider some arbitrary shape here that has a contact here and a contact here, and now we can simulate what the Hall voltage will be in a plus or minus field. So this is simulation, not the measurement now. So this is what the actual current streamlines are from the simulation, and this is what this anti-symmetrized Hall voltage would be if you were to compute the difference between these voltage maps, and you get this, and they look basically identical, right? And so the point is that as long as you can conformally map this structure onto a straight channel, the technique is going to work for diffusive transport. So it's not sensitive to the geometry or any weird effects like that. So, but of course, if you have a Corbino disk, for example, it's not going to work like this, right? Because that's not conformably mappable onto a channel. But for most relevant geometries for these kinds of measurements, it's going to work nicely. So you can look at the line cut here and look at the current density versus the derivative of this guy, and they line up exactly right, both components in the x and y direction. So at least numerically, we prove that the technique works for diffusive transport. So I also want to say that This will also hold in the hydrodynamic regime as well. I mean, the question is, like, microscopically, why does this work for diffusive transport? Is that there's this local relation between the Hall voltage and the current, right? Electrons don't remember much about the walls because they scatter off of some other impurity, and this is what generates this local relation. So in the hydrodynamic regime, you'll also have this a restoration of this local relation. While the current profile itself won't have the exact same shape, you'll still be able to confidently say that by mapping this this Hall voltage, it will represent the local current. But of course, we're going to try to distinguish the ballistic regime from the hydrodynamic regime. So we want to ask, what about the ballistic regime? So that's in fact where this experiment was done in the ballistic regime. And you can compare a ohmic simulation or diffusive simulation with the ballistic, and you could say that the ballistic simulation more closely matches than the ohmic, although there's not a dramatic difference between them anyway, right? That's actually often the case for the current flowing through this kind of structure. But of course, this is probed pretty coarsely here. If you want to be more quantitative, there are going to be deviations, and those particularly as a function of magnetic field. And we're going to discuss all of this tomorrow in detail to really try to gain an understanding of what you learn by measuring in the ballistic regime. And keep in mind, the quantity we're really measuring is the Hall voltage, so like a component of the Hall voltage, not the current. Right? Yes?
So if you have electric field that drives the current, right, so that's the gradient, the field is the gradient of the potential that you measure. But there is also this diffusion that's current, right? So diffusion time, the diffusion time the gradient of the density. So if there's a deviation of neutrality, there are some other contributions to the currents. So did you consider that?
No, but I mean in the diffusive regime, for example, I can just say empirically our data will match diffusive simulation perfectly in the diffusive regime. So I think this like the quantity where the Hall voltage is accounting for all of this somehow self-consistently. But I'm not sure I understand exactly this distinction.
But you measure the potential, right?
Yeah, we measured the electrostatic potential. Yes, yes.
So the current has this field and the part that is driven by the gradient of the density. But that somehow is not...
Right, so I mean this is, in this regime the density is constant, right?
So there is a neutrality...
Yeah, sorry, yeah, so this is the, so if you want to compare the geometric capacitance of the backgate to the quantum capacitance of the device, and the smallest capacitance is going to dominate, right? So because the backgate isn't super strongly coupled to the device, the geometric capacitance is the smallest capacitance. So in this sense, you can pretty safely assume that you have uniform density throughout the device. Okay. Of course, it's super interesting to then look in a device where you have a really strongly coupled gate and to actually observe these kind of effects and to see how it would differ. But yeah.
Another point of clarification. When you say ballistic simulation there, you mean free path longer than the width of the channel, but shorter than the length of the channel? Yeah. That's a bit of a cheat in definition of ballistic, right? Because you started out by showing it's truly ballistic.
Yeah. So in tomorrow, in the next talk, I'll belabor this point further, that this is like as good as you can do, at least in graphene. That you're never going to be able to make a device that has dimensions that you can scan, at least with our technique, that is actually properly ballistic in the sense that the momentum non-conserving or momentum relaxing mean free path is much larger than any length scale in the problem. So, yeah. Okay, just a quick point about how sensitive this is for current imaging. Intuitively, you guess that by applying a larger magnetic field, you're going to increase the Hall signal, and this is going to give us better sensitivity, right? So you want to apply as large of a field as you can get away with. But of course, the larger the field you apply, the more you're going to perturb the flow through the device, right? you have, in a magnetic field, especially if you want to consider ballistic electrons, what's going on? The electrons are bouncing around on some cyclotron orbits, right? So you can guess that you want to keep the magnetic field at least a cyclotron radius larger than the width of the channel, right? This is, and if you want to be as minimally perturbing as possible. So just applying these constraints that we want RC to be like greater than W, and then based on the Hall voltage and the voltage sensitivity of our device, we can get an estimate like this. So for metallic samples, I think you'll get a current sensitivity that compares pretty favorably to other scanning probe techniques like scanning squid and V-centers. But for semiconductor systems where the density is orders of magnitude lower, I think our technique really excels because of just the way this scales. So for semiconductor materials, I think this technique is really powerful for imaging currents. Again, with the caveat that it's not really the current, it's this component of the Hall field, but we'll get into all of this in the next talk. Okay, so to sum up the main points here, we have this nanotube that we suspend on a cantilever, which serves to be our scanning single electron transistor, which is this super sensitive detector of electric fields. We can look at ballistic voltage drops in a sample. We can also apply magnetic field and image the current. So this is what's, again, most relevant for the hydrodynamic imaging. But I want to flash a couple of other results quickly that of just things you can do with voltage imaging in the ballistic regime of graphene. So nothing with hydrodynamics and nothing with current imaging. This is just how do voltages distribute spatially when you have a ballistic sample, and then you can create interesting geometry. So a very simple but still interesting geometry is this expanding channel where you have, so again, this is a graphene device here. The darker lines here are etches in the graphene. So you can flow electrons from here to here, and then it goes through this wider section here. And you can ask, how does the voltage drop, particularly around this corner here? So this is, again, for these hydrodynamic measurement predictions, you'll predict seeing these voltage whirlpools at these points, but you'll get exactly this kind of thing happening in ballistic flow. You see that the potential goes negative here, this dimple here, whereas in the diffusive regime, that doesn't happen. It just drops linearly. You can also take a straight channel, do this voltage imaging in a relatively large magnetic field, large in the sense that it's far away from the quantum Hall regime, so in this sense very small, but W over RC becomes, but by RC I mean the cyclotron radius, and W is the width of the channel, this ratio on the order of 2, something like this, then you can see what we're calling magnetic focusing peaks on this. So this is the voltage on one side of the channel, and on the other you see these oscillations, and this is oscillating because at different magnetic fields you get this combined effect of collimated electrons coming out of a contact and then bouncing around like this. But so if you want to talk to us afterwards about these results, there's lots more to say, especially Asaf, who's here in the audience, who did these particular measurements. So again, this is where we're going to get by the end of next talk, and I'll just leave this here as to linger. So, thanks.
Very impressive. I have
Thanks.
two questions actually. One question, you showed the Hall data. I was wondering this non-difference between ballistic and diffusive in the Hall data. If you play with the symmetric part of your result, so the magnetoresistance, would it also be almost the same for?
So the symmetric part is so the symmetric part is basically these colored lines here. So in a sense, the anti-symmetric part is the current streamlines, and the symmetric part is the potential drop.
Yeah, but I was wondering, so you have two data, one at plus
Yeah.
millitesla and
Yeah.
minus millitesla. This is the difference between.
Right. So the black lines are the difference between them, and these lines is the sum. The colored lines are the sum. This is the symmetric part, the colored
In
line.
simulation, do you see any difference between?
No.
The second question was,
Okay, at the corner. Yeah. Sorry, at the corner they drop. Yeah, that's the yeah.
there should be, because I think But the second, thermal gradient. Have you thought of putting a thermal gradient and looking at layers and, instead of Hall, it would be layers and then...
I'm typically wary of these kind of, they sound hard to be able to...
So the reason I'm asking question is there any ambipolar effect? In the sense that when you go very close to the neutrality point, then you have also electrons and holes. Of course, if you look at electron imaging, I mean, electrically, you cannot make any difference between holes going this side and electrons going this side.
It's not totally true, actually. I mean, in magnetic field, you can, and especially you can imagine geometries with superconductors in particular, where you can use Andreev reflection to kind of split the electrons from the hole and see these sorts of effects. So there are ways to measure this, but in terms of thermal measurements, I think there's plenty to do with electrical med, but this sounds like a challenge. I mean, you know better than anyone, right?
One question? So it's not my question, but someone asked me about your previous page.
This?
No, the two.
This.
Yeah, this. So why on the y-axis it's not current, but...
Yeah, good question. So we'll address this directly in the next talk, but this is because this is the actual quantity we measure, right? So we measure the Hall voltage, right? And then we differentiate the Hall voltage in the y direction of the channel. So this is exactly what we measure. So then you want to be able to make a claim that this y component of the electric field is actually the current. So in the ballistic regime, it's not. And in fact, the difference between the y, this becomes the critical factor that allows us to discriminate between hydrodynamic and ballistic. The current profile, the rigorous current profile, looks very similar to this at both 4 Kelvin and 75 Kelvin. But the point is that at 75 Kelvin in the hydrodynamic regime, EY really is Jx. In the ballistic regime, EY is not Jx. And the difference between these tells you that you're hydrodynamic instead of ballistic. So, yeah, but I'll explain this more clearly tomorrow.
Okay, if there are no more questions, let's enjoy.